All right, here's our electrostatics review. Now the first few questions are going to be general rules regarding electrostatic forces. Number one, we're looking for the charged particles that are exchanged. And my options are protons, electrons, and neutrons. It is the electrons that are responsible for the exchange between objects. And the reason that they're exchanged is because they are on the outside of the atom and take less energy to release or absorb from that object. Numbers 2 through 4 referring to the law of conservation of charge. Okay, so law of conservation of charge, we saw this when we talked about momentum. We saw this when we talked about energy, thermal energy. It's the same concept. The law, according to this law of conservation of charge, when a balloon is rubbed on the person's head, their hair becomes positively charged. So that balloon is removing the electrons. Therefore, the hair is losing electrons. Okay? So when the hair loses electrons, it becomes positively charged. When the balloon gains electrons, it is negatively charged. So as a result, the balloon becomes negatively charged by gaining those electrons, the same number of electrons. So in other words, if the hair gives up 100 electrons, that means the balloon is gaining 100 electrons. It's the same number. Now, the reason it does this is so that the total charge stays the same. So again, referring to my law of conservation of charge. So total charge stays constant. Okay, number 5. Which law describes our answer to number 4? Well, again, that's the law of conservation of charge, which says that total charge will remain constant. So if one object gains 100 electrons, another object is going to lose 100 electrons. So again, one object gains, the other one has to lose electrons in order for total charge to stay constant. Okay, number 2, list 2 examples of induction we've seen in class. Well, induction is when you take a charged object and place it near another object that is neutral, causing that neutral object to be charged. So an example of that would be sticking a balloon to the ceiling. Now, this is a misconception because people think, well, if I'm touching it to the ceiling, that's got to be transferred through conduction. That's not the case. That charge is being transferred through induction. You just can't see it as much when you just place it near the ceiling. So the reason we stick it to the ceiling is so that you can actually see that that ceiling or the wall has become charged. Okay, now in some things that you can see, if you charge a balloon and place it near a soda can, the soda can is going to move without even being touched. That's induction. If you place a charged balloon near the neutral water, the water is going to bend in the direction of the balloon because it is being charged. There, you are inducing a charge on that water, and it's a charge that's going to attract it to the balloon. So that is charge through induction. So this is not touching. Our second method is through conduction. Okay, conduction, which means direct contact. Now, 2 methods that we've discussed. If I rub a balloon on my shirt or hair, the balloon is directly rubbing the shirt or the hair. That's direct contact. It's building a charge. If I slide across the seat of a car, we showed you the video of the girl sliding across her seat, gaining a charge that she later transferred to her gas pump, which ignited the fire. But she became charged initially through conduction, through direct contact. Static discharge, anything that has a spark. Okay, so the Van de Graaff generator, when we had that going, there were sparks shooting out. That lady in the video, if she charged herself through conduction by sliding across the seat, that charge transferred through to her gas pump through the static discharge, which ignited the fire of the gas pump. And another one that we've all seen is lightning. Lightning is a spark that jumps from the clouds to the ground. Okay, so it's just a spark on a bigger scale. Number 9, if we're talking about charges, opposite charges will attract each other and like charges will repel. Okay, now all charges are surrounded by electric fields that are drawn from positive to negative, always positive to negative. Okay, so down here I've got a positive charge and I've got a negative charge. If this is true, if these field lines, the electric fields that are drawn, or that we're going to draw, move from positive to negative, here's my positive charge, here's my negative charge, they're going to move from the positive charge to the negative charge in that direction. Okay, always in that direction, positive to negative. So this is what the charges start to look like. Now, as they get further away, the charges are going to make bigger loops, but always from positive to negative. And these are going to come in. So essentially, I'm not going to draw them on here, but these lines are here, they don't stop. Okay, this line, if I was to draw it out, would continue going all the way up, all the way back around, and into this negative charge. Same here. It would come out of the positive charge, go all the way down and around to the negative, always from positive to negative. When a balloon sticks to the wall, it shows that static forces are stronger than gravitational forces with very little mass. So if you stick a balloon to a ceiling, gravity is still pulling it down. However, that balloon is not falling. So that proves to us that the electrostatic force keeping the balloon on the ceiling tile is stronger than the force of gravity, especially when these masses are very small. So we're talking about a balloon and a ceiling tile, or 2 electrons. Those are very small masses. We're not talking about the Earth and the Moon, or the Sun and Neptune. We're talking about tiny, small masses. Moving on into electroscope questions. The leaves of an electroscope. So the electroscope was that metal box that had glass windows and had 2 metal leaves hanging from it. So these leaves of an electroscope are going to react depending on what kind of object is placed near it. So in this scenario, number 12, the leaves of an electroscope will do what if I place a neutral object in contact with it? Well, the neutral object being touched to a neutral electroscope is not going to change anything. There will not be any change. There has to be some kind of a charge. If 2 objects are neutral, you won't see any change. On 13, however, I've got another electroscope, and this electroscope is neutral, but it's being touched by a charged object. So the charged object is going to transfer its charge into the electroscope, and without touching. This one says touch, but it can also be done without touch. And when those charges transfer through the electroscope, the leaves that are in that electroscope are going to spring apart. You're going to get like charges in those leaves, and they're going to separate. Number 14 is showing you just a raw diagram of a charged rod. So this is a positively charged rod, and it's going to be placed near the sphere. Okay, so here's the sphere, here's the positively charged rod. It's going to be placed near the sphere without touching. Okay, so these charges are going to transfer not by touching, through induction. Okay, so these positive charges that are up here are going to attract negative charges. So this sphere at the very top is going to attract all these negative charges. Now this electroscope was once neutral. Now that doesn't mean it was all negative. That means there are negatives and positives. So if all these negative charges are now up here at the surface, then all the positives that are in this once neutral object have to be down here in the metal leaves. Okay? So all these positive charges are going to be forced down into these leaves. And what we talked about before, when I have like charges, like these 2 positive charges, they are going to repel each other, which will cause them to separate or spring apart. Okay, so these leaves of the electroscope move farther apart when there are more or less charges applying a force to the electroscope. So let's say that there's a weak force right now. So instead of a rod, we just took a balloon. We saw that these leaves separated. If I took something stronger, like a rod that is charged, these leaves are going to separate even more when there is an increase in charge. Okay, so more charge means more separation. All right, so let's get into some of the math components of this. So what we're looking at here in Coulomb's law, and I'll show you, I'll write Coulomb's law for you guys. Coulomb's law says electrostatic force is equal to Coulomb's constant times my two charges, all divided by the distance squared. Well, this tells us that there are relationships. Not only can we calculate force, distance, and charge, but we can look at relationships between force, distance, and charge. Now, between force and distance, there is an inverse relationship. An inverse relationship between force and distance, meaning if the distance increases, the force gets weaker. Now, because my distance is in the denominator, the force is equal to the inverse square of the distance. Distance is in the denominator, and it's being squared. So force is equal to the inverse square of that distance, which only means that force is affected in a different way. Okay? So if I'm looking at how the force is affected when the distance doubles. When the distance doubles, what happens to force? So let's look at it. If I'm looking at only force and distance, we could say force is equal to 1 over d squared. Well, if my particles are doubled, let's use a 2 to represent doubling. In my equation here, I'm going to express it as 1 over 2 squared. And 2 squared is 4, so this means that my force is now 1/4 its original amount. Okay? It's 1/4 its original strength. Okay? 1/4 is the key here. Now, what happens if the force, or how is the force affected when the distance is halved? Well, we're going to go about that the same way. Force equals 1 over distance squared. If I'm halving my distance, that means I am at 0.5. So I'm going to plug a 0.5 in here for d. So I get 1 over 0.5 squared. Well, 0.5 squared is 0.25. And 1 divided by 0.25 is 4. So now that force is 4 times stronger. Okay, it is now quadrupled, 4 times more than what it originally was. Now, the opposite happens between force and charge, meaning opposite to force and distance. There is a direct relationship between force and charge. So, if the charge increases, my force increases. So 17a, we're looking at force and charge when the charge doubles. So I can express this as F equals Q1 times Q2. Well, if my charge is doubling, that's going to be a 2. So I'm going to express it as a 2 times a 1, because only one charge is doubling. And 2 times 1 is 2, meaning it doubles. The force doubles. But if that charge is halved, 0.5, then I'm looking at force equals 0.5 times 1, and 0.5 times 1 is simply just 0.5, or 1/2. Okay, so now it's half its original strength. So it is weaker. Now, what plays a bigger role? Well, because distance is in my denominator and it's being squared, then the distance is going to have more effect on the force than the charge is. Okay, so because distance is squared, it's going to have more effect on force. Okay. Number 20. Okay, so now we're actually getting into some calculations. Number 20 says, what is the force? So that's telling us we're solving for Fe between a negative 5e, negative 20 charge, so Q1, and a 1e, negative 5 Coulomb object, that is Q2, and they are 0.5 meters apart, that is distance. Okay, so using my equation, I'm going to start substituting. Electrostatic force is equal to Coulomb's constant, which is 9 times 10 to the 9th, times Q1, which is a negative 5, times 10 to the negative 20, times 1 times 10 to the negative 5, all divided by 0.5 squared. Okay? Okay, so if I start to simplify this a little bit, I'll start with the numerator. Um, 9e9 times a negative 5e negative 20 times 1e negative 5 gives me negative 4.5 e negative 15. And then the denominator, 0.5 squared, gives me 0.25. And then when I divide those two out, I get a negative 1.8 times 10 to the negative 14 newtons. This is my electrostatic force between the two. Okay, so now it's asking me, is this force attractive or repulsive? Okay, my first charge is a negative 5e negative 20. My second charge is a positive. When I have a negative and a positive, we know that opposite charges will attract. So it's going to be an attractive force. Okay, number 22, if two drops of hairspray repel each other with a force of 9 times 10 to the negative 13 at a distance of 0.008 meters, what is the charge on each of the equally charged drops of hairspray? Okay, so it's telling you that our force is 9 times 10 to the negative 13. They're a distance of 0.008 meters away, and they are equally charged. We want to figure out what that charge is. So Q is unknown. This is Fe. This is Q is what we're solving for. Here's D. Okay, so let's start to write it out. I've got 9 times 10 to the negative 13 equals K, which is 9E9, times, since both of my charges are equal, I'm going to express that in my equation as Q squared, divided by, and my distance is 0.008 meters squared. Okay, so I've got Q in the numerator, and it's part of a fraction, so I want to set up a fraction on the left by putting it over 1. So now I can cross multiply. So 0.008 squared times 9e negative 13, and when I multiply those two together, I get 5.76e negative 17. So 5.76e negative 17 equals, and 1 times 9e9q squared is just 9e9q squared. It does not change. So 9e9 times q squared. So I want to get q by itself, but it's being multiplied by 9e9. My next step is to divide both sides by 9e9. And I apologize for going into the next problem. Hopefully you have a little bit more space. So when I divide those two, this is going to cancel out. And so now I've got on the left 5.76 e negative 17 divided by 9e9. And when I divide those two out, I get, and I'll bring it up here, I get 6.4 times 10 to the negative 27. That equals q squared. My last step is to get q by itself. In order to do that, I have to take the square root of both sides. So I get q by itself now. And q equals 8 times 10 to the negative 14 coulombs. 8 to the negative 14. So is it attractive or repulsive? Well, I've got two charges. Both charges appear to be negative. So positive. So two positive charges will repel each other. That'll be a repulsive charge. Okay. So now I'm going to clean this up just a little bit so I have room to write. All right, there we go. All right, so what is the charge on two identical pieces? So again, these two pieces are going to be identical, and they're going to repel each other with a force of 10 times 10 to the negative 25th. So this is electrostatic force. They are 0.01 meters apart. That is D. I know what K is already. I want to figure out what the charge is. So Q is unknown. Okay, so if I write that out, I get my force is 10 times 10 to the negative 25th equals K, which is 9E9, times, since both charges are identical, I'm going to express it as Q squared divided by, and their distance is 0.01 squared. Okay, so again, I've got Q on the right, and it is part of a fraction. I want to make a fraction on the left so that I may cross multiply 0.01 squared times 10e negative 25. And when I do that, I get 1e negative 28. And then when I cross multiply the rest, 1 times everything on the numerator, I get 9e9 times q squared. It doesn't change. Okay, next step will be to get q by itself, but it's being multiplied by 9e9, so I need to do the opposite, and that's to divide by 9e9. So the two 9e9s cancel out. Okay, I'm going to bring this over here to the right. So 1e negative 28 divided by 9e9 gives me 1.11 times 10 to the negative 38. And that is all equal to q squared. And the last step is to get q by itself. The opposite of squaring something is taking the square root. So when I take the square root of the right side, I get q all by itself. And 1.11e negative 38, when I take the square root of that, I get 1.05 times 10 to the negative 19. And there is my charge for each identical piece of styrofoam.